Okay, so yesterday we were discussing this example semaphore where we have one queue and the transmitter is very fast. He transmits the data at a rate of one data every 1 nanosecond, but whereas receiver is slow, he will pop out data slowly. Now now what needs to be done to solve the problem of overflow over here? What according to you needs to be done to solve the problem of overflow here? Tell me. There is a transmitter, there is a receiver. Transmitter is giving data, or let me use a queue in between. Transmitter is giving data to the queue. The queue is a bounded queue at every 1 nanosecond interval, but whereas receiver is going to receive the data every 2 nanoseconds. So the transmitter is twice as fast as the receiver. Now in order to avoid the overflow of data into the queue, what needs to be done? Logically, forget semaphores or anything. What would you do if such a situation is there? That is, the transmitter is transmitting the data twice as fast as the receiver can receive it. And anyone else, I asked you guys to browse about the formula to calculate the size of the cube based upon the speed of transmitter and receiver, so that there is always enough space. There is always enough space available to avoid the overflow or underflow of data. Anyone has that? Fine. So now what would you do to solve this problem? Tell me quick. Can you guys hear me though? सो रहे हो क्या? Are you guys asleep? Fine, Saturday morning. Boring you guys with something? Then how would you solve this problem? Tell me. If the transmitter is transmitting data at a rate of one data every 1 nanosecond and the receiver is receiving, or he can process the data only one data after every 2 nanoseconds. This means transmitter is twice as fast as the receiver. Then how will you solve the problem? To slow down the transmitter, isn't it? First, to make sure to avoid the losing of data, we have used Q. Yes. Now for every data, it cannot do that. See, like Harsh is saying, wait till it takes. Okay, fine. Now, but for every data, you cannot do it. If you want to do it for every data, then why have Q in the between? Then why have Q in between? What you can do is you can slow down the transmitter to such a level that it gives one data and waits for it to be consumed by the other guy. That is, then you have to run your transmitter at a frequency of pound 2, not pound 1. But ultimately, that is not the goal. The goal is to give some back pressure. What is back pressure? Like you guys are doing ALU project. Yes, in that one there is a signal called as ALU ready. Now, if you have given an operation for which the ALU requires more time, more clock cycles to consume and cannot accept another data till then. So what it will do? It will generate ALU ready signal. ALU ready signal to be low. If the transmitter sees that the ALU ready is low, it will not give the next data, isn't it? In the same way, there has to be a back pressure mechanism. Let's say it accepts the first 4 datas or 5 datas. Then it has to wait till some time that there is space available. There should always be some space available. Yes, there should always be some space available. Now for that, what we will do is we have to slow down the transmitter. The receiver can run at its own pace. We need to slow down the transmitter. To slow down the transmitter, what we will do? We will make use of a semaphore, like that is lock and key mechanism. So in this one, I'm going to just uncomment. See, the transmitter needs a key to get access to the queue. Then what am I doing? I'm first waiting for this get. What is get? Get is not a function. It is a waiting task. It will wait till one key is available. As long as a single key is available, it will break, it will come out, it will push data and return the key back again. If I am to just run this, again my problem is not solved. Why? Because every 1 nanosecond, I will get the key, I will push the data and I will put the key back. The whole concept here to slow down the transmitter is to snatch the key from this guy, isn't it? Snatch out the key from this guy. Now, if he keeps getting the key for every 1 nanosecond, he has access to the queue every 1 nanosecond. He keeps filling the queue every 1 nanosecond. Then what's the point? Isn't it? In the same way, now to snatch the key from this guy, we need a manager that I've written over here. The third task. What this task does, it waits till the size of the queue is equal to the bounded size. Here you see the size is 4, the bound is 4. The bound for the rightmost index is 4. That means 4 plus 1. The size of the queue is 5. Now the moment the size of the queue becomes 5, what this guy does is it snatches the key from this guy. Now, then what it will do? It will wait for at least 4 elements or wait for size less than 5. So always there are 5 datas available in the queue. Yes, always there are 5 datas available in the queue. Now the moment there are 5 datas, you snatch the key, you wait till one data is pulled out. Then what you do is put the key back so that he keep filling the, so always the queue size will be 4 5 4 5 4 5, because the transmitter is twice as fast, right? So you need to give him some buffer space, via like this. So let us save this. I come back and see if the problem is solved. Now the main key here is this: get and put are waiting task. Why is get a waiting task? It will wait till one key is available for him. Put, it will wait till it can put the key back. In the same way here, it will wait till one key is available to him. If both, again, it will wait till the size is reduced to less than 5. That means the receiver to pop one element from that one and then put it back. So mathematically, how is this going to be? See, you'll put one data, you put two data. By the time you're putting three data, the, what do you say, where which color? Okay, then the receiver is going to say 0.1 pound 2. You're putting the second data, the receiver is going to receive this data, so this data is gone. Again, when you're putting this data, the when you're putting this data, the receiver is going to get this data. When you're putting this data and this data, the receiver is going to get this. Then when you're putting this and this, the receiver is going to get this. So every 2 nanoseconds, you have 4 in the queue, you have 4 elements in the queue, and one is being popped out. So only for the last case, when you're popping out and you're pushing in one data, the size is exactly equal to 5. And over time, see, then again you will put two more datas, 9 10. You will pop out this one. So now what is the size of the queue? Exactly 5. Then what you do? You put in these two datas. The receiver is going to pop out this one. Now what is the size of the queue? 6. Isn't it? Now there is one data overflow here. So what I'm trying to say is, over time, this slow, or what is that, the slow nature of the receiver is going to keep accommodating the data into the queue. As long as the data is less than 5, we are okay. The moment it becomes 5, we snatch the key from the transmitter and make him a little bit slow, and then put the key back. Yes, there will be a race condition. If both of them try to access the key, there will be a race condition, 100% sure. Now see, that is the reason you have to make sure in a code you write it in that fashion. See here, this guy gets the key, then this guy pushes the element. Now the moment he pushes the element which makes the size of the queue becomes 5, he puts it. The moment he puts it, I am already waiting for it here. See that problem, you should make sure that you don't create that race problem. You don't create that race problem. If you see my coding here, this guy pushed the data, the size of the queue became 5 immediately. So the moment size became 5 immediately, now I am waiting for the next key. I am waiting for the next key. But there is no key available because the size just became 5. He comes here, he puts the key back. So immediately I grab it and I come and wait in this statement. Then he goes to forever and then this guy is waiting now. Now this guy is waiting. So there is no race condition in this example. Now this guy is waiting. Now while that guy is waiting, I am waiting for the receiver to pop one element. The moment receiver pops one element, I will put the key back. I will put the key back. So this is broken. Then he is pushing it. Then I am again waiting for it to become. Now again this push, if it makes it equal to 5, again I will break in and I will be the first one to get the key. So in your code you have to analyze and code it in such a way that you don't end up creating race conditions for the keys. You have to systematically program your code so that you don't end up creating race conditions for the access to the key. Okay, but good question. Now, did it solve the problem? Let's go ahead and find out. So, copy this. See, just understand the logic behind this. Don't concentrate too much on this one. The reason I am saying is, in my years of experience, I have never used a semaphore. I repeat, in my so many years of experience, I have never, yes, there are occurrences, there are places, but at your experience, no one expects you to use a semaphore and solve those problems because they will be at a very higher level. Forget it. All you need to do is use the next construct, that is a mailbox. The reason I'm suggesting that is because mailbox already has the queue and a semaphore both inbuilt. So you need not concentrate much on this one. Just concentrate to extent that you know how semaphore works. That's it. Nothing much. So let us come back here. What do we have here? Okay. Then we will see the output that the problem of overflowing of this queue is resolved. Then we'll go to the next semaphore example. Same thing here. What I've done is I've made transmitter a little slow. Receiver is too fast. So it will become an underflow problem. Again, to resolve that, what am I doing? Opposite. Just key access and put it back. So then what to do? Then first here we were waiting for the queue to become empty. Here what we will do is there we were waiting for queue to become full. Here we will wait for the queue to become empty. The moment it is empty, we get the key and we wait for at least one or two elements in the queue and then we'll put the key back. Nothing changing in these two examples. One is where the transmitter is fast and another is where the transmitter is slow. Both the condition. Just run these examples you and see this. You'll get to know. See, the problem of the queue is solved. See, the problem of the queues are solved. And also see here 50 nanosecond out of fork join. I have purposely added this join any 50 nanosecond out of this one. After 10 nanoseconds I'm disabling. So till that 10 nanosecond the receiver is receiving 5 data. See here, 1 2 3 4 5. This justifies that whenever for because of fork join any, if any one of the thread completes, you come out, the remaining threads will keep running as if you don't give disable fork. I repeat, if you come out of join any because of any one which being this here, if any one which being this here completes, then the rest of the threads will be still running if you don't give disable for. That is what I'm doing here. See, after disable for, I'm waiting for 10 and the receiver receives data every 2 nanoseconds. So it is printing this 5 data, and then I am disabling the fork. After disabling the fork at 60 nanosecond, I am giving 10 more nanoseconds. So is there any display after that? No. That means both the thread, all the threads in that fork got disabled, and then I am calling dollar finish. So with this, I am explaining you what a join any is as well. So what is the difference between fork join and fork join any? Fork join, let's say if this is a fork, join that, then there is thread A, there is thread B, there is thread C, and there is thread D. When will join come out? Join will wait for all of the data to come, all of the data to complete. So the join, if we are using fork join, it will come out at this time. That is, it will wait for all the threads 1 2 3 4 to complete. But whereas if you have joined any, it will wait for any one of the thread to complete. You see here, this being the smallest thread, if it finds that any single one of the thread in this 4 is completed, it will come out right away. Then it is called as join any. What is join none? Join none is, it will span all of these threads, it will span or it will start all of these threads and immediately come out here itself, and not wait for even a single one of them to complete, and not wait for even a single one of them to complete. It comes out immediately it starts, it comes out. So you should not use for join none and immediately use disable for. You have to time it right. See, the purpose of join any is to join none is to start all the things in parallel and not wait for any of them to complete and immediately come out. But if you are doing that and the moment it is coming out, you are using disable for, that means you are again killing all the threads. So you have to really have a choice, and it is not important that in case usage of don't just get this feeling or understanding that whenever I use join any, I have to use disable fork. No, no. Understand that no. It is only and only based upon requirement. Let's say if in join any you have one reset, you are waiting for reset. The moment you get reset, you come out and your driving logic, monitoring logic, whatever that is, needs to be killed. Use disable for. One classic example where you use disable for. Other places don't. Decide what you want. Is it clear, guys, how the problem of overflow got resolved in case of usage of semaphore? Now what I'm going to do is just introduce to you guys what a mailbox is. So I've shown you one example where the transmitter is fast, the receiver is slow, and the second example I'm not going to go through, I'm going to just brush it through as it is not important. So again, same thing, it's just that here the transmitter is slow and the receiver is fast. So whoever is faster, we need to slow them down a little bit to avoid the overflow and underflow of the queue. That is why this manager, the moment it sees that it is 0, it will snatch the key, it will make the other guy wait here. Then as the moment there are two entries, it will put the key back so that the receiver can get the key again and start popping the data out. So these are both the examples. Just I have made you both the examples yesterday itself. Please practice that. Now, what is a mailbox? Mailbox is these two clubbed together. Mailboxes, these two club together. Now there are two advantages of mailbox. I will go to the mailbox example. What is a mailbox? Mailbox is again queue. No difference between them at all, except for one. That is, there should be no overflow and underflow. Both queue and mailboxes are FIFO, right? The problem with the queue is queue could end up in an overflow or underflow scenario, but mailbox won't, because we have put and get as task, push back and pop front, push front and pop back. These four APIs are nothing but functions. They are not tasks. If they are functions, that means they cannot consume time. If they are functions, that means they cannot consume time. So now, in the same example, I have not done anything. The same example that we have for semaphore here, I've just merged these two and gave my declaration as mailbox. Mailbox is a class type. Understand that. It is a parameterized class. You remember, guys, when we discussed config.db, we created a parameterized class called as storage. Yes, same thing here. Instead of storage, the name is mailbox, and this parameter you have to pass the data type for the values that you want to store in. It can be a class, it can be a packed array like this, right? It can be anything, string, any data type, even classes, enums, anything at all. Any data type that you can think of can be passed here as a parameter. Declare it, and when you knew it with the size that you want to. Again, if you don't give the size, it becomes an unbounded mailbox. Unbounded mailbox is like an unbounded queue. So the size of is like a FIFO or a queue. So if it is unbounded, that means in theory the size is infinite. You can do that, but based for better performance simulations and all, you have to make sure you calculate the size right and prefer using queue. If you are in no position, yeah, you have a really small project and it is really not affecting you, you can create an unbounded queue. So for unbounded queue, all you need to do is use this for unbounded queue. Save this. Then again, same example, nothing changed. See, transmitter, instead of saying push back, it is using put. And whereas the receiver, who is slow, is using get here. No semaphore, nothing. No, same example. It's just that semaphore and queues are removed and use mailboxes. In queue, I was using pushback, and in pop front, whatever here in the receiver. Now here, what I'm using put and I'm using get. In this example, what was happening was we were making only one guy wait. That is the transmitter. Whoever is the faster, we were making him wait. But whereas, and the what see here, you guys never observed. I am waiting for 2 nanoseconds and then popping. Why not pop first and then put this 2 nanosecond delay here? What would happen? Let me ask you this question again. Can I just move this guy over here and then leave with it? If I just run this example, what to expect in the output? Tell me. See the code carefully, nicely, and tell me what to expect. Both forever run parallel. Yes. So both transmitter model goes together. Okay. Both run. So what? Analyze this. Write on the paper. Take a pen and a paper. Write it down. See what is happening and tell me what to expect. Yes, exactly, Pratik. They both start at the same time. no data will be popped because at the moment you start it is so in the same example you will get an overflow and underflow both the problems with the queue. So now here in the way I structured this example by putting this guy here, we never saw an underflow problem. But if you really see it, when they both start in parallel at the same time at zero time the receiver is also expecting a data and zero time this guy also wants to push the data. Again there will be a race. So for that I have put first delays. So if I just remove this delay here and get that here, put that here. Now what happens is, you see at the zero time I'm trying to push the data as well as pop the data. So there is a classic race. If push goes in first and then you get a pop, fine. If you pop goes first and then push back, then what happens? You will get a fatal error saying that trying to pop the data out of an empty queue. Isn't it? You will get that, isn't it? So now here, if you see, first I made you believe that only by slowing down the faster guy using a manager and a semaphore seems to solve your problem. No, again I'm bringing it back to you. This will not solve. Even now, if you use this, it will not solve the problem. Then how to solve the problem is to synchronize these two guys. How to synchronize? For them to wait and see how it goes. How? We need to not make just the transmitter wait, but we need to also make the receiver wait. So here, if in the same what it is, they both are trying to push. Now instead of using push and get, mailbox, see here, uses put and get. They both are waiting tasks. They both are waiting tasks. So this guy cannot put unless and until there is a space available. In case let's say the size becomes 5, it is full. It cannot put the sixth one unless and until someone pops it out. So that will wait. Here get. Even though get and put are called at the same time, put will put. But whereas get cannot get the data unless and until someone has put it. So already this will be synchronized as well. So at zero time and any time, get is a waiting call. It will not try to pop the data out immediately. But what it will do, it will wait till the data is available. But what will put to do? Put is also a task. It will wait. It will wait for what? It will wait till the space is available to be. It will wait till space is available so that you can put the data in. I repeat, put what will it do? It will wait till the space is available for you to put the data in. And that is how you synchronize both your transmitters and receivers and work with mailbox. Why? What are the advantages of mailbox? What are the advantages of mailbox? Mailbox has a semaphore and a queue in between. So both queue are FIFO. Queue could end up in an overflow, but mailbox uses put and get, which are that they will wait till the locations are available to either push or pop from the queue. Okay. On queue, there is no internal semaphore, but mailbox has an internal semaphore. You need to know these 3 points on the differences between the queue and mailbox. So we will run this mailbox example now and see how this one works. So let me fix this again to its original form, which we were discussing. Control Z. Okay. Save this, or else you will see a different result. Then you'll start scolding me and cursing me, saying what example did I give you guys. So we log mailbox. So again both the example. Fast transmitter, slow receiver. Mailbox 1, what will happen? Slow transmitter, fast receiver. No user semaphore, nothing. Everything still works. All you have done is synchronize them using semaphore, mailbox, which internally has a management for semaphore and everything. So we run this. Ruchita joined in today. Ruchita is there? No, she's not there. Okay, Kiran joined. Good. Kiran, any doubts, any concerns? Subha there. So what is this research? So next what we will see is what an associative array is. So we have seen what a fixed size array is, then we have seen what a dynamic array is, we have seen what a queue is, we have seen what a mailbox is, we have seen what a semaphore is. Now it's time for us to see the last element, that is the linked list, is what it is called as, which is nothing but an associative array. So if you see the associative array, it will complete the topic arrays and data types. Now we will then see how to mix these, create multi-dimensional arrays using us one dimension as associative array, another dimension as dynamic arrays. Because if you are the guys who wants to work on writing scoreboards, you need to learn this tricks. You need to implement this. You need to think in that way. See, we ran an example where transmitter is fast and receiver is slow. Did we ever get overflow and out of 4 gen? You see, for 10 nanosecond again the receiver is receiving all the 5 data. There is absolutely no problem or overflow nor underflow. Overflow nor underflow. Both the examples you have, mailbox and mailbox one, where the transmitter is fast, receiver is slow, as well as the transmitter is slow and the receiver is fast. You will never ever encounter. The reason you will not encounter is both put and get are waiting. Why? Because they both are tasks. Any doubts, any concerns, guys, in semaphores and mailbox and queue as well as dynamic array?